Okay, so we talked a little bit in the last hour about these units of area, converting square feet into square inches. And the reason behind it, of course, 1 square foot, we said was 144 square inches. And that comes from the fact that 1 square foot is 1 foot by 1 foot, or 12 by 12 in inches. We said that 1 square yard is how many square feet? 9. Again, 1 square yard, 1 yard by 1 yard, or 3 feet by 3 feet, or 9 square feet. You'll notice, by the way, the 144 is just 12 squared. The 9 is just 3 squared. Yes, whatever. Well, both of them are squared. 1 squared is just 1, right? If you have 1 foot equals 12 inches, you can square both sides of an equation and it'll stay true. So 1 foot squared is just 1 square foot. 12 inches squared, well, 12 squared is 144. Inches squared are square inches. And the same here. 1 yard was 3 square feet. So square each side. 1 yard squared is 1 square yard. 3 feet squared is 3 square feet. And we could keep going if we wanted to. I could do 1 square mile. Is how many square feet? You got it. 5,280 feet squared, or 27 million. Oops. 878,400. That is a lot of square feet. But it's 5,280 feet in each direction. And each one of those is a little square. So you're right. Those units can add up very, very quickly. And in a couple of days, we're actually going to look at volumes, looking at volume units and how that builds up. It's going to be very similar. Right now, I want to take a quick peek at the metric units. How does this all go with our metric units? So putting up our little chart with all of our prefixes on it for our metric lengths. 1 meter, of course, is 100 centimeters. 1 centimeter is 10 millimeters. That's just looking at the chart, right? If I have 1 meter, or from meters to centimeters is 2 spots to the right, so I move the decimal 2 spots to the right to get 100 centimeters, and so on. Well, what if it were 1 square centimeter? 1 centimeter squared. How many square millimeters would that be? Well, 1 square centimeter is 1 centimeter by 1 centimeter, which is going to be 10 millimeters by 10 millimeters, or 100 millimeters squared. When I look at this, just like in the standard units, all the conversions were squared. In the metric units, all the conversions were squared. When I was looking at units of length, anytime I moved 1 spot on the chart, I was multiplying or dividing by 10, right? Well, when it's areas, I'm going to be multiplying or dividing by 10 squared, or 100 each time I move a spot on the chart. 1 centimeter contains 10 millimeters. 1 square centimeter contains 100 square millimeters. So my conversions when I'm dealing with metric still use the chart, but if it's squared, if it's areas, each position on the chart is now multiplying or dividing by 100, or how many decimal places? 2. So 3.2 millimeters squared going into centimeters squared meters to centimeters is 2 spots on the chart, 2 spots to the right. So I have to move 4 decimal places. 1, 2, 3, 4. 32,000 centimeters squared. .052 meters into millimeters is, 3 spots. Meters to millimeters is 3 spots. That'd be 52 millimeters. But if it is .052 meters squared, going into millimeters squared, now 3 spots on the chart is going to be how many decimal places? 6 decimal places. So 1, 2, 3, 4, 5, 6. I got to add 3 zeros. That's going to be 52,000 millimeters squared. If I have 360 millimeters, how many centimeters is that? 36. On the chart, it's one from millimeters to centimeters is 1 spot to the left. That's 36 centimeters. But if it were 360 millimeters squared, bring the centimeters squared, now that 1 spot on the chart is 2 decimal places. So you're 1, 2, so it is 3.6. What do you think? Not so horrible? Oh, the centimeters and millimeters? Oh, nope. Let's take 48,000 meters squared. Convert it into kilometers squared. What's that going to come out to be? Well, from meters to kilometers on the chart is meters to kilometers is 3 spots to the left on the chart. So we're going to double that. It's going to be 6 spots. So 1, 2, 3, 4, 5, 6. It's 0.048. So what's that going to become? From meters to centimeters is 2 spots to the right, correct? But since it's squared, it's going to be 4. So 1, 2, 3, 4. Yep. 27,000.
What happens when we run into 2.7 meters cubed equals how many centimeters?
It doesn't sound like your classmates are ready for the answer to that question yet. So 480 centimeters squared, if I'm going to meters squared, is going to be how much? Centimeters to meters is 2 spots on the chart, so since it's squared, it'll be 4. 1, 2, 3, 4. Somebody asked, so why not?
Well, then it would be, all right.
Now it's going to be 10 by 10 by 10, which is how much? 1,000 or 3 zeros. So now each spot on the chart is going to be how many decimal places? 3 decimal places. So from centimeters to millimeters is 1 spot on the chart. since it's cubed, it's going to be 3. So 1, 2, 3. 31 millimeters cubed. Realistically, yeah, the metric is just you're multiplying how many decimal places you know. The metric system isn't bad. The standard system, yeah, it's worse. I mean, there's a reason why most of the world has decided the metric system is better than the standard system. I mean, I'm not saying I like one better than the other. I've used the standard system my whole life. I'm good at it. I don't mind it. But once you really get into the metric system, you can, if you objectively look at it, you can see some definite advantages to it. So 260 centimeters cubed going to meters cubed. Going from centimeters to meters is how many spots on the chart? 2 to the left, right? 2 to the left, correct? But now it's cubed, so we're going to go 3 times that. So instead of 2 to the left, we're going to go 6. So 1, 2, 3, 4, 5, 6. It's a drastic change, isn't it? But you've got to remember, instead of 100, now it's 100 cubed, which is a million. A million cubic centimeters in 1 cubic meter. We'll talk about the cubes, the volumes later. But since we've been talking about the areas, it might be nice to find out where areas come from. So we're going to take a look at geometry a little bit here, and we're going to start out with something like this. The absolute simplest concept in geometry is that right there. It's called a point. It is just a location. Has 0 dimensions to it. But even though it is the simplest construct, everything in geometry comes from it. For example, I can take that point and I can pull it in a single direction. Like that. Pulling in that one direction creates a length. And the length of that, we sometimes refer to it as a line, but technically in math, the line continues on forever in both directions. It's technically a line segment. But the length of that line segment is equal to the distance that we pulled the point. So we create a length by moving a distance. Notice we move in one direction, and no comments about boy bands, please, or I will freak out. Gives us 1 dimension. No, I'm depressed. I'm disappointed in myself that I even know that that's a band, put it that way. Put away your One Direction ruler and notebook and diary. So anyway, we moved in one direction, it created a one-dimensional object. Now a concept in geometry that's very important is the concept of perpendicular. You guys all know what a right angle is, correct? It's a square corner. Well, perpendicular is going to the next stage. You know, 2 lines that form a right angle are perpendicular. But there's really nothing more powerful there than just saying they form a right angle. But in 3 dimensions, let's say there was a line coming out of the page here. That line could form a right angle but not be perpendicular. To be perpendicular, it'd have to form a right angle in every direction between the line and the page. That's perpendicular. It's a right angle in every possible measurable direction. So if I take that segment, and we're just going to call it a line because that's what we generally call it in practice. We're going to take that line, that length that we created, and we're going to grab onto it, and we're going to pull it perpendicular. Now, 2 things are happening here. One is we are pulling it perpendicular to the original direction that we pulled it. 2, it is staying parallel to its original orientation. Notice it's always staying parallel to where it was at first. We're not twisting it or anything like that. And you think of that as taking a stick and dragging it across the sand, it's going to leave a shadow in the sand, a path in the sand. It's going to be a rectangle. That rectangle now has two dimensions because we pulled in two directions. So it has the original length, and it now has a distance that we pulled it that is often referred to as a width. The size of that, what we refer to as an area of that rectangle, depends on both the length of that original line and that width, or the distance that we pulled it. I often define that as a length times a distance, because when we look at other objects, there really isn't a width. So, for example, here, if I have a rectangle that's formed by taking a 12-inch line and pulling it 5 inches perpendicular, its area is going to be what? 12 inches times 5 inches. When we multiply the counts. 12 times 5 is 60. We also multiply the names. Inches times inches is inches squared, or square inches. But it doesn't have to be a rectangle. We said in our original thing that we pulled that length perpendicular to the original direction. But we don't necessarily have to pull it perpendicular. We can take that length and we can pull it at an angle like this. Notice, though, it's still always staying parallel to its original orientation. We're not twisting it, but we're not pulling it perpendicular anymore. We're pulling it at an angle. And let's say this is 7 inches here. If I go to find the area of that, is it going to be 12 times 7? Say no. No. What we need is the distance we have moved from our original location. That distance is always measured with that perpendicular again. To calculate an area, we must have two dimensions that are perpendicular to each other. So that may be 7 inches there, but that's not what we want. The distance that we move from where we started to where we ended, let's say that's 5 inches, that area is still going to be 12 inches by 5 inches, or still 60 inches squared. By the way, an old architect abbreviation for square inches and square foot, take the inch symbol, put a square around it, or the foot symbol, put a square around it. So if you ever see those symbols up here, that's what they stand for. I've tried to get myself out of them in the last few years. It took me several years to do it. I don't use them as much as I used to anymore, but it's kind of an old architect or structural engineering notation. Well, this is the inch symbol with a square around it, so that's square inch. And that's the foot symbol with a square around it, so that's square foot. So anyway, here, it doesn't matter that we didn't pull that line perpendicular. As long as we kept it parallel and we pulled it straight, it's the distance from where it started to where it stopped. In fact, we don't even have to pull it straight. Take my 12 inches here. Let's just do this. Now again, note that it's always staying parallel. I can pull it back and forth and whatever. Come on, get out of here. Like that. I'm going to cheat since I suck at drawing. Hey, look, I got both my sides exactly the same. But again, note that this always stayed parallel to the original orientation. What matters is not the length of this, obviously doesn't matter. What matters still is the distance from where it started. If that is still 5 inches, guess what the area is? Yeah, still 12 times 5, or 60 square inches. 60 inches squared. Think about it like this. If you think of, and this is actually kind of a calculus concept coming out here. This is as close to calculus as we'll get in here, by the way, so don't worry. If I think of this as being a bunch of really thinly sliced rectangles, I can take those thinly sliced rectangles and just kind of push them like a stack of paper. I just kind of push them over a little bit. And this is still just those thinly sliced rectangles. By pushing them over, the height is still going to be 5 inches here. Doesn't change the height. Doesn't change the area of the end, it just changes the appearance. Well, same thing down here. I can still have those thinly sliced rectangles. They're just kind of pushed in weird directions. It's still the same area on the end, same height. Well, what if we have a triangle? What if we have 16 feet here, and this is, well, let's go with 6 feet. Well, the only thing that we have area defined for is basically a rectangle or derivations of a rectangle. So to find this area, I have to define it in terms of a related rectangle of some sort. There, it's a rectangle. What's the area of that rectangle? Well, 16 feet times 6 feet. But the triangle that I'm really looking for isn't a full rectangle, is it? It is half of it. So I just divide that by 2 or times a half or whatever. Gives me 48 feet squared. So how do I find the area of this one? 11 times 18 or 18 times 11, either one, divided by 2. So 99 inches squared. Very good. How do I find the area of this one? So which two? I multiplied 24 times 10 is what you're saying? Yeah. Divided by 2. Give me 120 inches squared. How did I know to use the 10 and the 24 and not the 26? These two form the right angle. These are the two that are perpendicular. And again, we can only find area. To find area, we have to have 2 dimensions that are perpendicular. So what if we have a triangle that doesn't have any right angles in it? Can't do it?
Not that way.
Move on, try something different.
You make one in the middle?
Let's say that this is 24 inches here.
I think I know how to do it.
And let's say that this here is 9 inches. Well, again, we're looking at a related rectangle. Since we have this length here, let's make the rectangle off of that length. It's going to look something like that. So I have the 24, I need this distance, which would be the width of that rectangle. In the triangle, I would find that right here. This is the furthest point away from the side that I have, the base of my triangle. I need to find the distance of that, and of course distance is always at a perpendicular. So I have my 2 perpendicular dimensions. If I find that this is 5 inches, now I can find this area is 24 inches by 5 inches divided by 2, which is going to give us 60 inches squared. Again, I always have to have 2 perpendicular dimensions, and they have to be the dimensions that define that related rectangle.
So for any triangle, you can do it.
Any triangle I can find the area of as long as I have those 2 perpendicular dimensions. But here, the 9 didn't do me any good.
Yeah.
Don't care about the 9. I just threw that in there to try to screw you up. Triangle like this. What's that? let's say that's 12 feet across there. The related rectangle is actually like that. Now you might be looking at it saying, how on earth is that the related rectangle? Well, it is.
Oriented different.
It's just oriented different. What's that? Well, I could cut this all apart and show you how. But it gets kind of complicated.
You're good at getting that shit out the can.
Yeah. The height we need is this height right here. From the extension of our base up to this furthest vertex or furthest corner of the triangle. That'll define that rectangle. And let's say that that is 4 feet. So the area here is 12 feet times 4 feet divided by 2, or 24 feet squared, 24 square feet. You get confused.
How did we get the 4 feet in?
How did you get the 4 feet? Well, I had to give you the 4 feet. 4 feet is the distance from here up to the peak.
How did we calculate it?
You can't calculate it right now. I had to give you the 4 feet.
I'm trying to figure out how the pieces fit in there and make it so that
Well, I have the right angle on the down there. Use the hammer. No.
So
It
the
is.
top,
The right
the top
angle.
triangle,
Yep.
like you can make a straight line, that's where that will.
Here, let me do this for you.
The right angle is.
Here's the triangle, right?
You take a perpendicular line from that left point and a horizontal line.
Like this, right? Cut this across here. What we have is two triangles. This triangle here is half of the big rectangle, right? So let's do this. Let's say that this is 12 feet here, from here to here. And this is our 4 feet. Okay. This dimension here doesn't really matter, but let's call it 5 feet, just for sake of arguments. That red triangle, this one here that I just put in, is half of the big rectangle, which is 5 plus 12 is 17 by 4, right? This triangle here is a piece that's missing. It is half of the 5 by 4. Correct? I'm subtracting it out because that piece is missing.
Right.
Stay with me. I'm separating out the 4 over 2. So I have 17 times 4 over 2 minus 5 times 4 over 2. I can just subtract the 17 and 5 gives me the 12 times the 4 over 2. Now I realize that's kind of a complex algebraic function I just did there. It's a reverse distribution. That's why I hesitated to show it to you. But it does work out. It is still 12 times 4 over 2. It's just you have to go to the bigger rectangle and subtract out from the littler rectangle. You're taking this big rectangle, half of the big rectangle, and subtracting out half of the small rectangle, which ends up being half of the other rectangle that was there before. That's kind of complicated, I know. But you guys asked. You forced me.
He asked.
It's not my fault. Do you see it now, sort of? Kind of? Yeah.
Can you scroll back up for a second? One more. That 5 inches right there.
I had to give that to you again.
Right. That's called a chord.
No, that's not a chord. A chord is on a circle. That would be called a height or an altitude.
Altitude. What? There was a formula for calculating altitude, right?
Only if you either have the area in the base or if you're using trig. Then you got to use trig till next semester. Come next semester, we'll figure out how to do that.
I did a little bit of that. Thanks.
Yeah. Yeah, come next semester, we'll figure out that a little bit. We're doing some geometry right now, yep. Trapezoid. I tried to make sure I made it a little bit uneven there. A trapezoid, what's that? Well, some of them I don't intend to, they're uneven, huh? A trapezoid has two sides that are parallel. They're called the bases. So let's say the top of this one, let's call it 12 inches. And the bottom of this, let's call it 30 inches. Those are my two bases. And we'll have a height here like this, which I'm going to call 15 inches. Now, just like with the triangles, we only know how to find the area of a rectangle. So if we can turn this into a rectangle to find its area, we can maybe come up with a formula for it. What I'm going to do is this. I'm going to go halfway down this side. Somewhere here, I'm going to chop this off square. If I flip this little piece up, it should fit in here just perfect to fill that in. Right? If I do the same down this side, right here, go halfway down, chop it off square. This piece should flip up perfect to fill that in. So now I have a rectangle. Well, the height of my rectangle is still 15, right? The length of my rectangle is somewhere between 12 and 30. In fact, I cut it halfway. It's exactly halfway between 12 and 30. To find halfway, I average them together. 12 plus 30 divided by 2 would be 21. So the area of this, 12 plus 30 divided by 2 is 21, times 15, which is 315 inches squared. To find the area of a trapezoid, B1 is just base 1, the small base. B2 is the big base, divided by 2. In other words, you're averaging the bases and multiplying by that height. Oh, you're going to get homework on it, don't worry. Plenty of homework.
Not worried about homework. I'm not really like homework.
You know, I like homework. Such faith you have in me.
Yeah, it helps me with my.
So let's say this is 9 feet and this is 31 feet. And we have a height here of 12 feet. How do we find its area? Talk me through it. What's that?
Cut your.
Now, we don't even have to cut it. We just know it's going to be
You're gonna do half that triangle, go straight down.
okay. We know this is going to form a rectangle, and the length of the rectangle is the average of the 31 and the 9, right?
It will be drawn over all of your tests.
That's fine. So you're going to average the 31 plus 9 divided by 2, and then multiply by the 12. So 31 plus 9 is 40, divided by 2 is 20. Warning, by the way, when you punch this in the calculator, do 31 plus 9, hit equals before you divide by 2. If you don't, it's going to try to tell you that it's 35.5, because it divided the 9 by 2 and added it to the 31. So you do 31 plus 9 equals, and then divided by 2. And then times 12 gives us 240 feet squared. I'm going to have you try one quick in your notes.
Parallel line.
Yep. Try that one. How am I going to set up this area? Eight plus 16 over 2 times 25. 8 plus 16 is 24 over 2 is 12 times 25 is 300 square inches. How many got 300? You see what you did? Yeah. You got to take the two bases, got to be the two that are parallel. Well, let's take.
I did two triangles.
Two triangles will work if you do it right, but it's tough because this doesn't necessarily line up with that.
I did the base, I did 8 times 25, divided by 2, I remembered that number.
Yep, and then 16 times 25 divided by 2. In this case, that will work, but not necessarily in every case. Let's step it up a bit. We talked about circles a little bit before. Area of a circle. Okay, we all know that the area of a circle is pi times radius squared, pi r squared. Or of course, the radius is the difference from the distance from the center out. We've talked about the circumference being pi times diameter, or 2 times pi times the radius, because the diameter is just 2 times the radius, right? So I replace the diameter with twice the radius. There's a reason why I'm pointing this out right now, because we're going to figure out where this formula came from. Why is that the formula for a circle? So let's take a circle, pretend that's round, with a radius r. I'm going to take the circle, I'm going to cut it in half. Now I'm going to look at half the circle. Now the distance around the whole circle, the circumference would be 2 times pi times r. What's the distance around half the circle going to be? If I divide that by 2, it cancels out the 2, right? That's just pi times r. So now what I'm going to do is I'm going to take that half circle and I'm going to cut it in really thin pi wedges, like this. Really thin. Again, that calculus thing, you cut stuff in thin enough slices. I'm going to fan out those pi wedges like this. Now I'm going to take the other half circle, I'm going to cut it in really thin slices, equally thin slices, so that I can fan out those pi wedges, and I can slide them in like this. Now what I've made there, if I cut those wedges thin enough, is approximately a rectangle. Assume that these are straight and I don't suck at drawing. This dimension right here is the radius of the circle. What's this dimension here? Well, that's this dimension here, right? Pi times r. To find the area of a rectangle is length times width. So pi r times r is pi r squared. So even the area of a circle can be brought back to a rectangle.
How can you have a straight line on the top and bottom when you know these
If you cut them very, very, very thin, that's what the theory the theory of calculus is you keep cutting them thinner and thinner and thinner until they're infinitely thin. Because you're right, there's a little radius. Let's say you cut it in half. What's going to look like that? Well, you cut it in 4. Well, now that's going to be closer to a straight line. Cut it in 8. The thinner you cut it, the closer it gets to a straight line. If you cut it infinitely thin, which is what calculus is, once it's infinitely thin, then it's a perfectly straight line. But I know what you're saying. It's not a perfectly straight line because there's little arcs there. But
Is there a formula to find out how thin they have to be to make it a straight
infinitely thin. No, you have to have an infinite number of little slices, is what they're saying.
Is that why it's pi?
Yeah. That's part of where the pi comes from. So anyway, if I have a circle with a radius of 5 feet, its area is going to be pi times 5 feet squared, or approximately 78.5 square feet. So I'm going to have you guys do circle with 8-inch diameter. Find the area. So it's pi times what?
16,
Pi times 4 squared. Where did the 4 come from?
half.
8's the diameter, so 4 would be the radius. So that'd be 50.24. You use the pi button. I just used 3.14 when I did it in my head. But yeah, if you use the pi button, it's 50.265. Okay. One last little thing I want to mention. Once we get into units, you can talk about pressure. Pressure is equal to a force times an area. PSI, pounds per square inch. Actually, not force times, it's force divided by area, I should say. If I have 400 pounds of pressure, and it's over 10 square inches. So it's 400 pounds of force, and it's over 10 square inches. The pressure is 400 pounds divided by 10 square inches, or 40 pounds per square inch. So if I have a cylinder so I've got a pump that's putting fluid into this cylinder through a hose, and this is developing 60 psi, pounds per square inch. And let's say that this here is a 12 square inch ram. That'd be about a 4-inch diameter ram. The amount of force generated is equal to the pressure times the area. So 60 psi times 12 square inches, going to give us 720 pounds of force generated. Okay, with all that thrown out there, it is time to give you homework. There's going to be 2 sections of homework. Some out of the big book, and some out of the little book. But you got the whole weekend to do it. And I know you had nothing better to do this weekend than math homework. On page 249, exercise 8-5, 1 through 23, the odds, just the odds. Page 250, exercise 8-6, the odds. On page 269, exercise 9-5, the odds. And on page 270, exercise 9-7, the odds. And in the little book, it is simply unit 30. You got to remember, I didn't give any homework in the first hour. That's 2 hours worth of homework. Basically 2 class periods worth of homework all at once. So don't panic. I did give you a minute to start on your homework if you want.
Oh, thanks. Take that long to put my notes in my bag.
That page 270 or page 27?
That should be page 270. There should be a 0 there. Thank you. Got it all down?